moving on to next topic, which is force experienced by a charge which is moving in a magnetic field. Okay, one of the most important topic of this chapter or unit. See, how does this charge experiences the force? Consider this is a uniform magnetic field, alright. Which direction this field is? I can show you like very good animated diagrams of this chapter, but end of the day, you have to explain the same things in your answer sheets. So what we are improvising on, I am explaining you the whole chapter on this whiteboard, which is something which you guys are going to replicate in your exams, and you're going to actually understand from these topics. But at the end of these topics, I'll also show you all the animated diagrams and everything possible, because when you Google some things on physics, you get every detail, right? So I'll try to show you as much possible picturizations of the concepts as possible, which will help you further absorb these topics in the best possible way. For now, consider I have a charge Q which is moving in this uniform magnetic field with velocity v. The magnetic field is B. According to the law and the theorem of this force, the force experienced by this charge is directly proportional to, first of all, the magnitude of charge. Bigger the force, more will be the charge, or more will be the charge, bigger will be the force experienced by it. Proportional to Q is also proportional to normal component of velocity. This velocity vector will have two components along the field, perpendicular to the field, the normal component, and lastly magnetic field. More the magnetic field, but obviously more will be the force experienced by the charge. So if I combine all these three factors, I'll get F is what? Proportional to Q VB sine theta. I have to put a constant of proportionality, which is K Q VB sine theta. What is K? In SI system, for the first time, good news, in SI system K is equal to 1. So F is equal to QVB sine of theta. This is the formula for force experienced by a charge which is moving in a uniform magnetic field B with a velocity V. This thing can also be written as this equation QV cross B, that is the cross product of these two vectors, right? Now, if the cross product is like this, remember +1 when you did the cross product of two vectors. Suppose this is vector A and this is vector B. This is angle theta. Cross product of vector, the direction of force was given by, or direction of the net answer was given by what? The resultant. From the right hand, take the curling of fingers from vector A to vector B, like A cross B means A cross B, from A to B, and thumb will give you the direction of the resultant. Exactly, that was +1. Now we have deduced another direction thing, another direction formula method, which is called Fleming's left hand rule. This is the direction of force. Okay, this is the magnitude of force. Carry on, where direction of force is given by what? Fleming's left hand rule. Okay, what is left hand rule? If you stretch first finger, the thumb and the middle finger of your left hand, then or such that the first finger points towards magnetic field direction and the thumb points towards the direction of flow of charge or the direction of flow of current, then the thumb will give you the direction of force experienced by the charge, that is force field current, like this. Okay, force field current. So I'll just explain you with this example. I don't know the direction of force here, so how do you put this force field current thing? First of all, first finger is force, sorry, it is the what? Field. Field is perpendicular inside. Then current is, if this is a positive charge, the current is in the direction of flow of charge. So this is the direction of what? Current, this one. So thumb automatically gives me the direction of force experience. That means this is going to experience, this charge is going to experience a force in this direction. It would want to go in upward direction, but what will happen? This is not a car that it can steer around and go in this direction right away. No, it will experience a force in perpendicular direction due to which its direction will change. But even at this direction, if I apply a force field current, the direction of force again goes changing and again and again. So every time the force is perpendicular. So I have made these directions in this much huge gaps, but if I make these directions at every point, it will ultimately be a circle. So these are all acting like a tangents on the circle, and that is what the direction of the definition of circle was, right? All the tangents, the locus. Anyhow, for right now, this diagram clearly elaborates that a charged particle undergoes a circular path when placed in a magnetic field, right? So if there is a circular path involved, that means there will be some tangential force also involved. So this next part, which we are going to study right now, will give you something very important. Note it down, and I am rubbing it. See, I am leaving this formula only. Force field currents F is equal to QVB sin theta, or I am rubbing this also, and I will give you the answer. When, now you know two things. Number one, the force has a magnitude and a direction. This direction is given by Fleming's left hand rule, which gives thumb, first finger and middle finger, right? First thumb gives you the direction of force, first finger field, middle finger current. Magnitude is given by F is equal to QVB sin theta. Till here it's very simple, and next part is even simpler. If the tangential force, if the centripetal force, okay, why do we need to introduce centripetal force always when there is a circular motion? What is centripetal force? If you guys are not yet clear about centripetal force, I'll give you a brief explanation. Centripetal force is the force which causes the circular path, number one. Number two, centripetal force is always given by some other force. Okay, it is always provided by some other force. For example, in case of this electrons and protons, electrons revolve around the nucleus in circular orbits. If this is circular motion, there is a centripetal force involved, and as I just told you that centripetal force is provided by something here, the electrostatic force of attraction is providing you the necessary centripetal force. When planets are revolving about sun, then the gravitational force of attraction is providing you the necessary centripetal force. When I tie a stone in a thread and I revolve it like this, then the tensional force produced in the string provides the necessary centripetal force. So make this point like very clear. This centripetal force is always provided by some other force, but we also have the formula of centripetal force, which is mv square upon r. So it is easier for us to deduce an expression for other quantities which are involved in any kind of circular motions. For example, consider this case. Whenever a charge is placed in a uniform magnetic field, or when a charge is moving, not placed, my statement was wrong, because if the charge is placed in the uniform magnetic field, V would be 0, F is equal to 0. Now, if a charge is moving with a velocity V in a uniform magnetic field, what will happen when it is placed in non-uniform magnetic field? We will come to it. In a uniform magnetic field, then the force experienced by it will be QVB sin theta, which is the magnetic force, and that force is responsible for the centripetal force required for the circular motion. So centripetal force is provided by here magnetic force. mv square upon r is equal to QVB. I am not using sin theta right now. I'll tell you why. Remember this formula, guys. This formula can actually produce all other formulas. Let me show you how. First, I want to find the value of V. Cancel out V from here, V from here. You are left with what? M V upon R equal to QB, or QB into R goes there upon M is equal to value of V. Second, if I want the value of R is MV, cancel out V square, it's like 1V and this V. You are left with MV here and QB here. R is MV upon QB, right? Number 3, when you have R, you can you find out T? What is time period? Time period is total distance upon total time taken. Sorry, time period is not total distance. Time period is distance upon speed, right? Speed is distance upon time, so time is distance upon speed. Distance is circumference, which is 2 pi r upon speed v. Now, in this expression, either put the value of r or put the value of v. Don't put value of both from those 2 points. Okay. So 2 pi, instead of r, I am using mv upon qb and upon v. V cancels out. T is 2 pi m upon qb. This is number 3. Number 4. If you have time period, what is frequency? 1 upon time period. That means qb upon 2 pi m. Fifth, what is angular frequency? 2 pi nu. That means 2 pi into this thing. 2 pi gets cancelled out. You get qb upon m. This is angular frequency. So guys, I strongly suggest you not to remember 1, 2, 3, 4 and this 5. These 5 formulas, please don't. Just remember one formula, and according to situation, just figure out whatever the formula required for a numerical or the expression is. Alright. So this formula straight away is applicable in the working principle of cyclotron. What is cyclotron? I'll just explain you.